Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability. This is the fourth lecture on queuing. In the last lecture, we did see the Poisson process, its definition, few postulates, and based on the postulates of the Poisson process, we saw the derivation of the number distribution of the Poisson process, which is a counting process, and presently we will see the properties of Poisson process. Just to recall the postulates of the Poisson processes, we saw the independence postulate, which says that the counting process NT is independent of the number of events that have happened prior to the interval T. And the second postulate talks about homogeneity in time, which says that the probability distribution to be dependent on the length of the interval. And the third postulate is on regularity, which says that probability of one occurrence in an infinitesimal interval of length h is given by lambda h plus order of h. So, based on these three postulates of the Poisson process, we saw the derivation P and T equal to e power minus lambda t power n by n factorial, and n can take the value 0, 1, 2 etc. Now, presently we will see the properties of the Poisson process. Here we have fundamentally the additive property, which is very important and facilitates the analysis or the modeling of several queuing models in networks, involving networks which is series or parallel and so on. So, these properties of Poisson process are very fundamental and very important, particularly in queuing theory. Now, this additive property says that sum of two independent Poisson processes is a Poisson process. So, suppose in a network, queuing network particularly, and these systems are connected in series say, then we are interested in the arrivals to the system, to the network, and the departures that take place outside the system. Now, the problem is the characteristics or the performance measures that one would be discussing for the entire system depends on the performance measures of the individual counters or the subsystems in the system. So, these performance measures are particularly if they are assumed on the Poisson process, then we can say that the pooled Poisson process will again be a Poisson process. So, that is how the arrival process, the departure process, everything can be modeled as a Poisson process. So, how you are able to model that is dependent on this additive property. So, that is why this first property, that is on additive property, is very important. Once again I repeat, if you are talking about two independent Poisson processes and say with the parameters individually lambda 1 and lambda 2, then the sum of the two independent Poisson processes will also be a Poisson process. The intensity parameter will be the sum of the two parameters lambda 1 plus lambda 2. So, a possible generalization of this additive property is possible, that is given by sum of independent Poisson processes n1 t, n2 t and so on n with mean values lambda 1 t, lambda 2 t and so on lambda n t respectively is also a Poisson process with the mean lambda 1 plus lambda 2 and so on plus lambda n into t. Now, how this comes, namely the mean, you know that if x is a Poisson random variable, then the probability mass function is given by e power minus lambda, lambda power n by n factorial. So, presently I am talking about the Poisson distribution, Poisson random variable. What is the mean of a Poisson random variable? It is lambda. Now, presently we are talking about the Poisson process. So, where the intensity function is lambda, namely the parameter is lambda and the mean is lambda t, because the distribution is p n t. We saw the derivation, p n t is given by e power minus lambda t power n by n factorial. So, the mean is lambda into t. Suppose we are talking about the pooling of the several random processes with the respective parameters, say lambda 1, lambda 2 and so on lambda n, then we have the mean of that total pooled process would be lambda 1 t plus lambda 2 t and so on lambda n into t. So, that is what the result says here, lambda 1 plus lambda 2 and so on lambda n whole thing into t. Next property speaks about the difference of two independent Poisson processes. So, it is given by n1t minus n2t. So, that is n1t is one Poisson process, say with parameter lambda 1, n2t is another Poisson process with the parameter say lambda 2. Then we have n of t, which is the difference between the two Poisson processes, namely n1t minus n2t. This is given by the distribution of this quantity event is given by p of n t equal to n equal to e power minus of lambda 1 plus lambda 2 into t into lambda 1 by lambda 2 whole power n by 2 into I of 2 t into root of lambda 1 lambda 2. This I mod n is the Bessel function of order n, and n equal to 0 plus or minus 1 plus or minus 2 and so on. But particularly if we have the counting process, because we are talking about the difference here, that is why the negative values have been listed here. So, what is important here to observe is the distribution is not a Poisson process, only the sum of two independent Poisson processes is a Poisson process, whereas the difference between two independent Poisson processes is not a Poisson process. That was another distribution. Next property speaks about the decomposition of a Poisson process. Here we are interested in, namely a random selection from a Poisson process yields a Poisson process. Suppose that Nt, the number of occurrences of an event E in an interval of length t, is a Poisson process with parameter say lambda. Suppose also that each occurrence of E has a constant probability p of being recorded, and that the recording of an occurrence is independent of the other occurrences and also of the counting process Nt. If m of t is the number of occurrences recorded in an interval of length t, then m of t is also a Poisson process with parameter lambda p. The continuation of this property says that the number m1t say of the occurrences that have not been recorded will also be a Poisson process, but with parameter lambda q. What is q here? Q is 1 minus p. P is the probability of getting recorded, q is the probability that the occurrence has not been recorded. So, lambda q will be lambda into 1 minus p, and here mt, the number of the counting process which records the occurrences, and m1t, which is the counting process which records the non-occurrences of the events. So, these two processes, they are again independent. So, as said earlier, the intensity parameter of mt would be lambda pt and that of m1t would be lambda qt. So, these two are again independent. It is something like you have some events happening, and any event that arrives, that happens, can get registered. So, what we are interested here is what is the counting process that is associated with the number of registrations. You see, every arrival need not get registered, and if it get registered, then it happens with probability p. If it does not get registered, then that happens with probability q. So, what we are talking here is what is the distribution of the number of occurrences or the events or the arrivals that have got registered. So, this counting process would be Poisson, but with the intensity parameter lambda p t. So, the parameter is lambda p, the mean is lambda p t. So, this is the property 3 and 4 together. Next property says that the Poisson process can be linked with a binomial distribution. So, this again we have, suppose NT is a Poisson process where S is less than T, then P of Ns equal to K given that Nt equal to N is a binomial distribution. This probably we saw in the last lecture. So, here S is less than T, under the knowledge that at a greater instant of time some n events have got recorded, we are asking for in a event prior in a time interval length of S that has occurred prior to the length T is given by the binomial distribution. So, that is the property. This property basically illustrates the importance of the Poisson process linked with a binomial distribution. The next property is if NT is a Poisson process, then the correlation coefficient between NT and N of T plus S is given by square root of T by T plus S. So, here the correlation coefficient we all know is given by covariance of say NT comma NT plus S divided by standard deviation of NT into standard deviation of N of T plus S. So, we have to calculate these expressions, namely the standard deviation of NT, NT plus S. As discussed in the last episode, we saw that suppose you are fixing the time t, the counting process NT becomes a random variable. Similarly, N of T plus S, when you are fixing the instant T plus S, then N of T plus S becomes a random variable. In this way, we are dealing with two random variables here. So, it is quite appropriate here to talk about the correlation coefficient between the random variables NT and N of T plus S. So, we can calculate what is the covariance of N of T comma N of T plus S, standard deviations, plug in that, we can get the quantity as resultant as square root of T by T plus S. So, observe that the whole thing is in terms of the time instance or the length of the interval. So, it is T divided by T plus S whole power half. That is the expression we have for the correlation coefficient between the two random variables N of T and N of T plus S. The seventh property is a very important property which is excellently used again and again in queuing theory, that too particularly in respect of the Markovian queuing models. So, what does this property say? It says that the inter-arrival times of a Poisson process with intensity parameter lambda obeys an exponential probability law with mean 1 by lambda. Here we have basically that the counting process which is associated with the events is a Poisson process. So, these are the number of events which happen along the time axis from time to time. So, when we say N of T, we are saying that we are talking about a length of the interval T. What are the occurrences, how many occurrences that have happened by time T. So, but then this has the link with the inter-arrival times. So, that inter-arrival times will be a sequence of random variables and they are nothing but the exponential random variables with parameter lambda, and we have the mean of the exponential random variable to be 1 by lambda. So, at this stage let us take a short break. Welcome back after the short break. We were looking into the important property of a Poisson process in terms of the inter-arrival times of the Poisson process, which I said it is very important in the queuing theory particularly in respect of Markovian queuing models. So, what happens here? We have the information about the underlying counting process which is associated with the arrivals is a Poisson process. That is, the process counts the number of events as the events keep happening. So, the count increases by 1 every time an event happens. But here this property particularly links the inter-arrival times. What are these inter-arrival times? The time between an arrival and the next immediate consecutive arrival. So, the time between two consecutive arrivals is a random variable now, because the events are happening randomly over the time axis. So, the time between the origin when the system is installed or when you start observing the system at time, say we mark it as t equal to 0. So, at the origin the counting starts, and at the first instant of time, say t1, the event happens. The time between 0 and this time point t1, we designate it as a random variable x1. So, next we look into the time between the first arrival and the second arrival. So, say the second arrival happens at time t2. So, that is another random variable x2. In this way, you have a sequence of random variables x1, x2 and so on. But once we have a random variable, we always associate or think of a distribution. So, the distribution what we associate here is the exponential random variable or the exponential distribution. So, this property particularly says that if the counting process associated with the arrivals is a Poisson process with the parameter lambda, then the inter-arrival times are exponentially distributed with the same parameter lambda. But we all know that for an exponential random variable, the mean is 1 by lambda. Hence, we have here the property is being listed here as, namely the inter-arrival times of a Poisson process with intensity lambda obeys an exponential probability law with mean 1 by lambda. So, next we will see the much awaited queuing models. For this, we need the basic derivation of the generalized Poisson queuing model. So, we are into the generalized model, then we will see the derivation of the number distribution of this model, and as we see consecutively each model, we are going to see 6 models here. So, we will look into the main derivation of the number distribution and then we will apply each model, what is the arrival rate and the departure rate there, and plug into these general distribution model which we are going to see now, and then proceed further. So, to start with, let us look into this generalized Poisson queuing model, where we assume that n is the number of customers in the system. Lambda n, we assume that it is the arrival rate of the customers, but under the knowledge that there are n customers already in the system. Similarly, mu n is the associated departure rate of the customers, given that n customers are already there in the system. Pn is the steady state probability of finding n customers in the system. Now, the basic assumption, we are saying this is a generalized Poisson queuing model. So, here we have the arrivals to be Markovian, the service times are exponential, which says that the counting process associated with the departures is once again a Poisson process, and the number of servers, we do assume it is only single server in the system, and the queuing discipline adopted is a general discipline, and there is no restriction about the capacity of the system. So, it is taken as infinity. Similarly, the source from where the customers come, the arrivals come to the system, there is no limit even there. So, in the Kendall's notation, we are looking into the generalized Poisson queuing model, namely Mn m suffix n slash m suffix n slash 1 colon GD general discipline infinity infinity. So, this is the generalized Poisson queuing model notation. So, next we will see, because we have said about the Poisson assumption here about the arrival process and the departure process, we are looking into the assumptions here, namely probability that no arrival and no death in the interval of length h, namely that interval is t comma t plus h. This is given by 1 minus lambda h minus mu h plus order of h. And here if you look into the assumptions here, in the last model what we saw was about the Poisson process. So, the derivation we saw there, we were looking into only one type of event. So, we had only one parameter there, probability of no arrival in an interval of length h was given by 1 minus lambda h plus order of h. Here we have included one more event, namely the death here, so or the departure. Basically here I would like to mention these arrivals in general are termed as the births, namely that event which increases the count in the system. Usually an arrival or a birth, they do increase the count. Similarly, an exit or a departure, similarly a death decrease the count in the system. So, these births and deaths can be termed as arrivals and departures. So, that is why we have here now two types of events. One is associated with the arrival, the other one is associated with the departure. The parameter lambda we said is associated with that of arrival and mu is associated with that of departure. Hence, we have probability of no arrival and no departure, but the length of the interval is h, that is the same, which is very small. So, we have 1 minus lambda h minus mu h plus order of h. Next, we have associated with this is in general when you are talking about just the probability of no arrival and no departure in an interval of length h. Suppose we are interested in finding this, writing down this rate, namely probability that no arrival and no departure in an interval of length t to t plus h, but under the information that conditioned on there are already n customers at time t. That is, here you are making the arrival rate and the departure rate to be dependent on the state of the system. Here the state, I mean the number present in the system at time t. So, that is n. So, under the knowledge that given that the number present in the system is n at time t, probability of no arrival and no departure in that very same h units of time is given by 1 minus lambda n plus mu n into h plus O of h. You see the similarity here in the previous line, we have the rate to be 1 minus lambda h minus mu h. There is no dependency on n, there is no suffix there, but here we are making the arrival and the departure rates to be dependent on the state of the system at time t. Another difference is here we have expanded it, namely minus lambda h minus mu h, here we have combined it, that is the only difference, otherwise the concept is the same. The next assumption here is probability of one arrival and no departure in the interval of h units of time. We are here writing it as an unconditioned event. So, the rate is or the probability is lambda into h plus O of h. One more thing I would like to remind you at this stage is the rate when multiplied with the length of the interval gives you the probability. The rate is here arrival rate per unit of time is lambda. So, when you are considering the length of the interval to be h and multiply that rate with h, then it becomes a probability. So, we have probability being written here of one arrival and no departure in T to T plus H is lambda H plus O of H. Now, we are making it state dependent. So, we do write the same thing when we are conditioning on the number of customers present in the system at time t. So, that is given by P of one arrival and no departure in the interval of t to t plus h under the knowledge that there are n minus 1 customers in the system at time t. This is given by lambda n minus 1 into h plus order of h. So, this order of h, once again I would like to recall, it is nothing but based on the regularity postulate of the Poisson process. So, it is like we are considering the h to be very small. So, we are only going to consider the possibilities of either probability of only one arrival happening or no arrival happening, but we cannot, we are not including the probability of more than one arrival or departure happening in the interval of length h. So, that all those probabilities are being absorbed into this quantity using the regularity postulate, which is denoted by O of h in the expressions. So, next we will see more than one arrival and departure in the interval of length h. So, that is P of k arrivals and no departure in the interval of length h is given by this k can be anyway, that is more than 1 when I say it can be 2, the count can be 3 or 4. We are not restricting about the number of events happening in general. So, we consider all these events are mutually exclusive, and hence when you are writing the probability of the mutually exclusive events, we get the sum of the individual probabilities. So, that is what is being written here, that is sigma k equal to 2 to n P of k a, that is k arrivals in the interval of length h into probability of 0 departures in the interval of length h, because we are writing the probability of k arrivals and 0 departures. When you see the events arrivals and the departures all are both are independent. So, it is like you are having probability of A intersection B where A and B are independent. So, that result is nothing but P of A into P of B, and hence we have this expression out here, namely sigma k equal to 2 to n P of k A into T in the interval T to T plus H into P of 0 departure in the interval T to T plus H. Now, this is nothing but order of H. We have seen in our previous assumptions, namely probability of k arrivals or k departures happening in interval of length H is given by O of H. Summing up all the probabilities, all these are getting absorbed into this quantity O of H. Hence, this has been written as O of H, and probability of 0 departure in the interval of length H is given by 1 minus mu H plus order of H. So, this should be finally, because we already said O of H when multiplied with any quantity, it comes to as O of H because of negligibility here, or in other words again bringing in the regularity postulate. Next, we see sigma k equal to 2 to n P of 0 A and k departures in T to T plus H is once again given by 1 minus lambda H plus O of H. It should be mu H here, 1 minus mu H plus O of H into O of H, which once again reduces to O of H. So, finally, we have similarly we can extend this in terms of the state dependency here, bring in that we are now ready to write this probability of 0 arrival and 1 departure in the interval of T to T plus H, but under the condition that there are n plus 1 in the system at time t. This is again written as mu n plus 1 H plus O of H. Why do you write this mu n plus 1? Because we have n plus 1 is the number present in the system at time t. So, we are making this probability to be state dependent here under the condition that there are n plus 1 customers in the system at time t. So, the rate is mu n plus 1 into h plus order of h. So, at this stage let us stop here and continue with the derivation in the next lecture, but before closing what all we have done today. So, we have looked into the most important properties of Poisson processes in terms of pooling of Poisson processes, linking Poisson process with binomial distribution, and then we saw the difference between two independent Poisson processes is not a Poisson process, and the most important property we saw that the inter-arrival times associated with a Poisson process will be an exponential random variable, or that distribution would be an exponential distribution, but with the parameter lambda same as the Poisson process parameter, and the mean is 1 by lambda. Thank you very much for your attention.